Now again, we have an example where we want to calculate partial derivative. Using the definition, using the limit definition. I'm not sure we've got the whole limit definition on the screen here. We should know from the geometry, at least from this picture, what we're going to do. We're going to do the rise over run and let h approach 0. And you should never do one of these without thinking that picture. You want that picture to be totally ingrained. That picture. Less so the formula. Let's just use this formula because it's visible on the screen. Okay? Or the formula down here for the partial with respect to x. Don't just use that formula blindly. Think about what it means. Go back and in your mind, picture this. And if you can't picture it in your mind, sketch it, because you can sketch it in just a few seconds to remind yourself. Don't sketch it just once. If you're doing 10 problems, sketch it for every problem until you say, I don't need to sketch it, I can visualize it. Now, if you're really bad at visualization, then if after sketching this thing 10 times you still can't imagine it and you still take time to sketch it, well, sketch it at least once a day, okay? To remind yourself that there's a picture that goes with the derivative. Don't just be content to do a calculation and leave it at that. Think deeply about what the calculation means and visualize as best you can. This advice, I think, will improve your performance in the course and also your understanding, so you don't come out of this course with no more understanding than you came out of the calculus course. Okay? And your understanding is always lacking. Everybody, almost everybody. 1 person in 1,000 really understands what a differential is. You're going to understand it because it's coming up right here. Okay? And it's very simple. All the differential says, if you move h units, you go up by this much. That's it. That's the picture. And that's a picture of the tangent line. Okay. We haven't done the tangent line, but if you understand what we did here, I chose to do the tangent plane, didn't want to do both. Because if you understand one, you can understand the other. The tangent plane's a little harder to understand than the tangent line, but the tangent line is just a line through x naught, y naught, f of x naught, y naught, parallel to that tangent vector. You learned earlier easily how to do the equation of a line to a given point parallel to a given vector. And if you didn't learn it, if the whole process doesn't come into your head right now, when I say that, you didn't learn it well enough. Not saying there's anything wrong with you or you're evil or anything. Don't think anybody is. Just saying, be fully prepared for the test, which will come up after this chapter. You want all those images. You want all those connections, all those pictures. Because after this chapter, of course, it's hard. Okay. It doesn't get that hard if you're well prepared. It gets a little harder. It's a fairly easy chapter. Okay, partial f with respect to x. End of advice. The beginning of calculate the partial derivative. Is what? Well, I'm just going to write it out. What's the derivative with respect to x of x squared? 2x. What's the derivative with respect to x of xy? Now remember, the partial derivative with respect to x, we get it by holding y constant. When we slice the thing, you can't quite see it. I guess I'll move over a little more. When we slice this thing to calculate the partial with respect to x, it was in a plane where y equals y naught. Y was constant. So we treat y as a constant. So the derivative of xy is just y. And if the derivative of x times 3, it'd be 3, right? Derivative of x times a, where a is a constant, would be just a. And of course, it's a negative derivative. And then we do the same thing here. We hold y constant. We treat y as just another symbol that isn't changing. there we have it. And then partial depth with respect to y. Well, we have no y dependence in x squared. X squared doesn't change when y does, so its rate of change is 0. Negative xy gives us a negative x. And then 3xy squared gives us 9xy. Just totally straightforward. We're just doing, each partial derivative is just a plain, simple derivative. You just got to remember to treat the other variable as constant. And it takes about 2 problems to get used to that, because that's just mechanical. Unless I ask you to do it by the limit definition. Okay, well, let's do it by the limit definition. It's going to be the limit as h goes to 0, and sometimes I'll write as delta x goes to 0, because h is just a change in your value of x, and it can be written either way. Okay, so this is where, and the last problem in the homework for today, people have trouble with this. But it's just, right there it is. Okay? We're just asking you to do a limit. Now the limit has a meaning. So use that problem to do the whole meaning of the limit, and the whole definition of partial derivative, and all the way up through the tangent plane. And implicitly the tangent line, which we didn't do, but comes right out of the same picture. Okay, what's f of x plus h? You plug x plus h in for x, you get x plus h quantity squared. I suspect at least some people did x squared plus h instead of squaring x plus h. And function notation does not work that way. Okay? So you've got to understand the function notation. But if you plug in everything correctly, I don't have room to write the whole thing, so. Okay, this whole thing over h, right? So expand x plus h, there it is. And then it's minus xy minus hy. And then this is the first term, and here's the second term. Mark out all this as a term and all this as a term. Okay, so the first expression and the second expression where I distributed the negative through. Actually, I focused on this, didn't just write it down as my hand wanted to do, so I think I probably got it right, but we'll see. So we divide all this by h. Well, what's that? Well, we notice, and I'll color code this because I really hate to draw lines through things that people don't cancel right, although I think you guys would. We got x squared here and negative x squared here. So x squareds add up to 0. And then we've got a minus xy and a plus xy. And basically everything over here is going to cancel something over here. Notice I said cancel in undertone because I don't like the word. Everything over here added to something over here is going to give you 0. That's what cancellation means. Again, I'm sure you know that, but I want to emphasize it because people will, even at this level, sometimes totally violate the spirit and rules of cancellation. Okay. So there we have it. All we got left is this, 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 and this, right? That leaves us 2xh minus hy plus 3xh, and I didn't leave out the h squared, I just want to tack it on the end. And you know, talk about being careful about the way you write things out. I've been doing this. I get tied up in the algebra and I forget to write limit, right? It's a limit as h goes to 0. And I don't know how I'm going to get limit as h goes to 0 in here. It's going to have to be a pretty small number. I took my calculus course 57 years ago. I was in that calculus course. So like a lot of people, I keep forgetting to write the limit thing here. So this is not really a good thing. Forget, but okay. So now reminding ourselves that this is a limit. Because when we get down to the end and have to take the limit, you look back here and see we don't have the limit indicated. It's that point. Okay, well then, and that's the limit. As h goes to 0, well, we just divide h into every term. The division distributes over addition, just like multiplication, because division is just multiplication by a reciprocal. And h is non-zero. It's going to approach 0, but it'll never be 0. Okay, we get 2x minus y plus 3x and I left something off. See the y cubed here? I had it here. I didn't put it here. And I should have had it here. Okay. Then h goes into h times. And what's the limit? Well, there's no h in any of these, so all these are going to be part of the limit. And as h goes to 0, the h here disappears. Okay? So what's this? I got the y cubed in the wrong thing. When I distribute here, I'm going to get a 3h y cubed. And where is that going to go? 3hy cubed. I was being careful. Okay. It's 3x y cubed h. 3h y cubed. And there's no x in it. where should that go? I've got 3xy cubed here. And then I got 3xh. And it should be 3hy cubed. So it'd be a 3hy cubed. Let me rewrite that to make it look better. Okay, so once again, there's no x in that. I have a 3y cubed. And now this matches this. Anyhow, that's how the limit works. It's going to match. The reason this is because of this. And if you think about what's going on here, you see that we're holding y constant. And by holding y constant, these three terms will be matched by three terms of the opposite sign in the rest of the expression. So they're going to go away, leaving you just a bunch of multiples of h or higher powers. Multiples of h, the h is going to just divide out, and you're going to end up with that expression. Higher powers of h, the h is going to divide into the higher power and give you some power of h, which go to 0. So that's it. That's how you prove these things, how you work these things, and that's how you work that last problem. And of course, I believe you're going to have problems that you need to work in the present section where you use the limit. So it's just a typical illustration. They get more complicated if you got sines and cosines and exponentials and stuff like that. Then you know, your algebra gets a little tougher, and you got to use tricks and some of the trig formulas, whatever. Okay.